Good morning, physics scholars. So uniform circular motion. It's motion that involves objects moving in a circle, and what makes it uniform is the circle has constant radius and the motion of the object has constant speed. And that doesn't mean constant velocity. We know it's not constant velocity because the object is changing direction. That's what causes it to move in a circle. And so an object that's moving in a circle like this is experiencing an acceleration that's center pointing. It's called centripetal acceleration. Centripetal means center pointing, pointing toward the center of its circular path. So in this tutorial, we're going to take a look at a special kind of uniform circular motion, the motion of a satellite orbiting Earth in a circular orbit. And we're going to take a look and see what are the parameters of this orbit that give rise to a special condition called a geosynchronous orbit. And geosynchronous means the orbit occurs in a period that's equal to one Earth day, 24 hours. And then there's a special kind of geosynchronous orbit called geostationary orbit, which is a satellite that's orbiting the Earth with an orbital period of 24 hours, but the orbit is directly above the equator. So that means the satellite orbits the Earth in exactly the same period that the Earth rotates on its axis, and because it's above the equator, directly above the equator, it's always above the same point on the Earth's surface. So that's called geostationary. All right, so let's do this. Okay, so here's a little picture of the Earth with a satellite, and the satellite's moving in circular orbit. So it's going around the Earth in a circular path, and as this is happening, the Earth is also rotating. And so geosynchronous orbit is one where the period, the amount of time it takes to go around this orbit, is equal to 1 day, 24 hours. So what we want to do here is let's use the physics of uniform circular motion to then calculate, well, if it takes 24 hours to go around, what is the radius of the circular path? And the radius is called little r, is not the same thing as the altitude. Altitude would be distance above the Earth's surface, but the radius of the path is relative to the center of the Earth. All right, so what do we know about the physics of this situation? We know that the rate of centripetal acceleration toward the center of this circular path is equal to the speed of the satellite squared divided by r, the radius of its circular orbit. Okay, and now we're going to have to do some additional physics, though, because if we want to solve for r, our goal here is to solve for r, we need to connect centripetal acceleration, speed, and radius. And the speed is pretty straightforward. So if you have something moving in a circle, its speed at any moment can be found by taking the distance it travels divided by how long it takes to travel that distance. So if you have an object that's moving in a circle, when it goes around once, the distance it traveled is equal to the circumference of its circular path, and the amount of time it takes to do that circular path is the period of its revolution. So the speed of a satellite in orbit is going to be 2 pi r, the circumference of its circular path, divided by t, the period of its revolutions. Okay, so we have v. We have a formula that we can use to find v. All right, what about centripetal acceleration, the rate of centripetal acceleration? Well, in order to find centripetal acceleration, we've got to use Newton's second law. So Newton's second law is going to tell us that the net force exerted on the satellite, I'm going to give it a C because in this case it's a centripetal force. It's center pointing. It's going to point toward in the same direction as the centripetal acceleration. Newton's second law says that's going to be equal to the mass of the satellite times its rate of acceleration, which in this case is centripetal acceleration. So what force is causing the centripetal acceleration? In this case, it's the gravitational attraction between the Earth and the satellite. So Newton also gave us a formula, his law of universal gravitation, that allows us to calculate how strong this force is. So in this case, the net force on the satellite is equal to the force of gravity, just to call it F sub g, between the satellite and the Earth. And Newton's law of universal gravitation says that that force is equal to the gravitational constant, big G, times the mass of the satellite, which here we'll call little m, times the mass of the Earth, we'll call that big M sub e, divided by the distance between the satellite and the center of the Earth squared, which is r squared, the same r that we had earlier. So this is Newton's law of universal gravitation, and this is the mass of the Earth, something we could look up. And this is a constant, the gravitational constant. We can look that up as well. Okay, but now, because of Newton's second law and the law of universal gravitation, we have a way of figuring out what the centripetal acceleration is. We can put these two equations together, and we have mass of the satellite times its rate of acceleration is equal to big G times the mass of the satellite times the mass of the Earth divided by the distance between their centers squared. An interesting thing happens here. The mass of the satellite is on both sides of this equation, so it cancels. It goes away. The mass of the satellite is not important to the answer of this problem here. And then what we get is the rate of centripetal acceleration equals big G times the mass of the Earth divided by the radius of the satellite's orbit squared. And now we have all the pieces we need to put them together to figure out what r is. So what should we do first? Let's do this. Let's take that equation and this equation and substitute in v equals 2 pi r over t to get rid of the v in the expression for centripetal acceleration. So we'll have a sub c equals v squared, so that'd be 2 pi r divided by t squared divided by r, which will simplify to, we'll have an r squared in the numerator and an r in the denominator, so that will simplify to 4 pi squared r divided by period squared, t squared. Okay, and then now let's equate this expression with this expression. So we have acceleration, centripetal acceleration equals 4 pi squared r over t squared, and that's equal to big G times the mass of the Earth divided by the radius of the orbit squared. So we have 1 r in the numerator on the left-hand side and an r squared in the denominator on the right-hand side. So if we solve this expression for r, we'll get an r cubed. Solving for r, we get r equals G times the mass of the Earth times the period of its revolution squared divided by 4 pi squared, and we got to take the cube root of that expression, which is the same as raising it to the 1/3 power. We look up these physical constants. G, the universal gravitational constant, is equal to 6.6 5.67 times 10 to the minus 11th, it's a very small number, meters squared, newtons times meters squared over kilograms squared. What about the mass of the Earth? Let's look that up. The mass of the Earth is 5.972 times 10 to the 24th kilograms. And what about the period of revolution? If it's geostationary or geosynchronous, which geostationary is a special case, the period of the revolution is how many seconds are there in an hour, which is 3,600, times 24 hours in a day, and that's going to equal 86,400 seconds. You put this all together into this formula, and the answer you get is the radius of this circular orbit that has this property of being geosynchronous is 4.223. Let's round it there. 0, 0, 0, 0. So that is 42 million meters, or 42,230 kilometers. So, if you look up the radius of a geostationary orbit, the answer you get is more like 42,160 kilometers. And the reason you get something that's a little bit different is because in order to calculate, so if you look up the actual value for a geostationary orbit, you get something depending on what the nature of that orbit is. If it's geostationary around the Earth, Earth's equator, you get something a little different than if it's an orbit around another axis of the Earth, or another plane of the Earth. And the reason is because the Earth, this equation is assuming that the force of gravity is constant everywhere, and it's at a certain radius from the center of the Earth. And that's not true, because the Earth is not a perfect sphere. The Earth is a little bit lumpy, and it bulges a little bit at the equator. Okay, but we get a really good approximation of what the geostationary orbital radius is from the surface of the Earth. Now, what would be the altitude of a geostationary orbit? In order to calculate that, you would take the answer we got and you would subtract off the radius of the Earth, and that tells you what altitude above the Earth's surface you should put a satellite if you wanted to orbit in a geostationary or a geosynchronous way. All right, so that's it for today. A little bit of new material here in the introduction of Newton's law of universal gravitation and applying Newton's second law to give us another route to finding the centripetal acceleration. All right, so that's it. I hope this helped, and I'll see you next time.